Whenever you need to calculate arc length of a parametric curve like this, the idea is kind of complicated, but the mechanics of it is always very simple. You just always directly apply this formula that you see in front of you right there. L, the length, equals the integral, and that's from a to b, from alpha to beta, is whatever bounds, limits of integration that you have. Right here, you have this integral from 0 to 3 is what I'm going to do. And then just do the integral of dx dt, or x prime, and dy dt, or y prime. I'm going to explain the idea behind this formula for a second very quickly, and then I'll solve this example that's on the screen with you. So the idea is not super complicated to understand, but proving it is a little bit roundabout. So let's say you have this curve right here, and you want to find the length of this curve. You do something that generally is very simple, very common idea in calculus. I wouldn't say simple, I would say common in calculus. You sort of divide the curve into shorter pieces, and then you estimate the length of each piece by approximating that using the length of lines, because those you know how to calculate. And basically, let's say this is your L1, this is your L2, this is your L3, this is your L4, this is your L5. So basically the idea behind it is that L is approximately the sum of Li from I equal to 1, 5. If you're not familiar with this, all this is saying is that this is L1 plus L2 plus L3 plus L4 plus L5. That's all this is saying, this summation notation here. Now, how can I calculate the length of each L1, L2, L3, L4, and L5 now? You use basic Pythagorean theorem. Let's say I need to calculate this first length right here, right? I can make a right triangle right there. Let's say if this is the change in y, and this is the change in x, then your Li is going to be, by using the Pythagorean theorem, you can say Li squared equals change in x squared plus change in y squared. So I'm also going to name this change in xi. So for L2, this is going to be change in x2, and this is going to be change in y2, because this is going to be one change in y, and then right here I'm going to have another change in y, and then right here I'm going to have a different change in y, another one right here, very small change in y. So for each L, I'll have a different change in x and a different change in y that I'll add all together. So that means if I take the square root on both sides of this last equation I wrote, Li is the square root of change in xi and change in yi squared. Okay, so we're not all the way there yet, because again, I'm talking about parametric curves. So right now x is a function of t and y is a function of t. So you can see that there's no t in there. But if you remember from calculus 1 that when you're studying differentials, delta x was approximately equal to dx, like this. And this is the same dx from u substitutions that was f prime of t dt, right? If you remember linear approximations and differentials. Again, remember, x is f of t, right? So it's like you're making a u substitution. And likewise, delta y is going to be approximately dy, which is now g prime of t dt. And when all of that goes back into this, you can say this Li is, so there's going to be a dt squared multiplying both of these. So dt squared times f prime of t squared, and then g prime of t squared. All of those underneath the square root, and this, because this is squared and it's multiplying this entire thing, it gets to come out of the square root, and I get to say this is f prime of t squared and g prime of t squared, all of that times dt. Okay, so this is your Li. In fact, this is just an approximation for each Li, and in fact, this is not just f prime of t, this is f prime of a specific t, some ti that's close to Li over there. But as you add them all together, as you add the Li's, you're adding these things, and as you make the number of divisions in your curve, so right here I've only used 5 L's, L1, L2, L3, L4, L5, but if you increase the number of divisions, each of those is going to get smaller and smaller, and then the approximations will get better and better, and this instead will give me the integral. So as the number goes to infinity, so I can say n goes to infinity, n being the number of divisions, this turns into the integral for arc length from alpha to beta that we were talking about, f prime of t plus g prime of t squared, both of them. So this is the idea. Like I said, the proof is a little roundabout. You don't have to know this proof. All you have to know is the formula. I think knowing the proof is helpful. I'm a mathematician. I like showing people proofs, but you can just immediately, if you want, calculate arc length by just using the formula directly. So I'm going to do that right now. So we're given this, x is this, y is this, and we're also given these as the limits of integration. All I have to do is I have to find dx dt. So remember what I said from the very beginning. X was f of t, y was g of t. So when I say f prime of t, I mean x prime. So I look at x, so isn't x equal to 2/3 of t cubed? Then x prime, or dx dt, will be 2/3 times 3t squared. The 3's cancel, this is 2t squared. And then isn't y equal to t squared minus 2? Then dy dt, or y prime, will be 2t. So now the length will be the integral, and from 0 to 3 of 2t, so big square root dt, the 2t squared from before, squared right here, this thing, and then plus, I have a 2t squared. And so this is all of it. Setting it up is something that's the new stuff, right? That's the only new stuff that you haven't seen in previous calculus classes, and now you just have to go through the motions and solve this integral. So maybe a little difficult. Let's go and get through it together. It's going to be integral 0 to 3 of square root 4t to the power 4 plus 4t squared dt. And I can see that I can factor out a 4t squared. So 4t squared here. I can do this and see it as a t squared plus 1, like so. And then, because these are multiplying, I can put 1 square root for each. So the first one is going to be 2t, and the second one is going to stay, unfortunately, as t squared plus 1. And then I have to solve this integral. This may be a little bit challenging at first if you're not very proficient with Calculus 2 integration techniques. And I also remember as a student making the wrong choices every time. I'd always try to use the most recent content I had learned. For example, I'd look at this and think of a trig substitution because I see t squared plus 1. I do, what would I do? T equals tangent theta or something. But I don't think that's the right choice on this one. I don't think necessarily that that would be also wrong, but I also think the best possible choice is a direct use substitution, t squared plus 1, which gives du equals 2t dt, which is exactly what's outside there. You see. So this is going to be u right here. Just the inside of the root is u. And these together will form my du. So my integral changes into the integral of u, square root of u, du, I should say, right? And now when t is 0, u is 0 squared plus 1 is 1. And when t is 3, u is 3 squared plus 1, so 10. So this is what I'm doing now. And this is an okay integral because this is u to the power 1/2. I add 1 to the power, becomes u to the power 3/2, and then I divide by the power. Dividing by 3/2 is the same as multiplying by 2/3, and then I have to evaluate that from 10 to 1. So I'll be all done with this length at the moment. So this will be 2/3 10 to the power 3/2 minus 2/3. When I plug in 1, this is going to be 1 to the power 3/2. It's going to be 1 anyway. So I'm going to leave it as is. Of course, you can factor 2/3 if you want. I won't be mad if you don't. But this is the correct length of the surface we just calculated. Sorry, not of the surface, of the curve. Another kind of interesting thing that's worth noting here is that this guy here has meaning. This thing here has meaning. This on its own is going to carry meaning, and it's going to help us find velocity most of the time. So let me continue with a couple of examples. So this is the same example I just solved, right? And the answer seems fine to me. If you see any mistake, I think those two numbers are equal, but if you see any mistake, you can always let me know down in the comments. I'd appreciate it. I'll go back and fix everything. But let me do this other example here, just so you see a different integration technique being applied. So we're going to do the integral again, of x prime squared, y prime squared dt, square root of all that, the entire square root, and that's from alpha to beta or from a to b, you decide. So that's going to be the integral from 0 to 2. I derive x, that's e to the power t minus 1, but that's still squared. And then I derive y, that's 1/2, that's 2 e to the power t over 2. So I need to multiply by 1/2 because of the chain rule. And then that's still squared. That's what I have to do now. So just double check. If you need to pause and derive things yourself, double check. E to the power t over 2 here, deriving that requires me to use the chain rule. I set u equal to t over 2, and then u prime is 1/2. And that comes down and multiplies by 4 to give me this too. So double check the derivatives if you need. Sometimes I'll make mistakes on those. I appreciate you pointing them out. Now 0 to 2. And now big roots. Now I have to FOIL this first number. This is going to give me square root of the first 2 e to the power t. This is a negative right here. And then plus 1. All of this is just me foiling this. So again, double check. Foil it yourself. And then squaring the second one is a little easier. I just square the first one. Square 2, that's 4. And square e to the power t over 2. Just power of a power, just multiply the powers. It's t over 2 times 2, which is just t. And then that seems like a very difficult integral to solve, but in fact it isn't. You can just combine these two terms right here. To get the root of e to the power 2t plus now 2e to the power t plus 1. And now it still seems like you're stuck, but if you remember the foiling that I did right here, when I foiled from here to here, what did I use, right? I used that idea that a minus b squared is a squared minus 2ab plus b squared. And so I ended up with this that's in green there. But if you pay close attention, you see that changing this negative to a positive just changes this negative to a positive. And so you would end up with exactly this. You see? This is exactly the same as this, the only difference being the plus and the minus. And because I know this came from foiling, then that means this will be the exact same as this by just changing this minus into a positive. So I can rewrite this integral, and then I'll be almost done as integral 0 to 2 e to the power t plus 1 now squared. And now I get to cancel the root and the square. So we'll stop for a second and see if you understand. Maybe even FOIL this to see if you go back to this to double check how I saw it. And now finally I can just antiderive as normal. E to the power t, antiderivative is e to the power t again. And then t evaluated from 0 to 2. Plug in the 2, that's e squared plus 2, minus plug in the 0, e to the power 0 plus 0. So that's e to the power 2 plus 2 minus 1. That's e squared plus 1. That is the exact length of the curve.